So, hello everybody. My name is Traianos, and I'm working for HELLENIC Cables, Greece, as a design engineer for the last 2 years. Today, I will present you a work prepared from our team regarding proximity effects in Trefoil cable arrangement, EMTP simulation versus experimental validation and power frequency.
This is a small glitch. It's not sharing the correct screen. Now it should be okay. It's okay, Jesus?
Yeah. Perfect. Thank you. So at first, I will briefly describe you the contents of this presentation. I've made a short introduction about high voltage AC cables and the physics that are very useful in order to calculate losses appropriate, and how you can model it in EMTP. And finally, we will make an introduction about the measurements. The goals of the study is to make a validation through measurements for an unarmored cable, typical for underground installations, and for a submarine cable, which is, of course, armored. The theoretical background will be explained, and the measurements procedure and the conceptual setup will be shown in this presentation. Of course, the EMTP modeling is very important in order to validate our results, and then the comparison between the results and measurements will be presented. Finally, we will have the conclusions of this presentation. To begin with, the underground high voltage cables, AC cables, are used, and its use is increased in recent years because of the growing urbanization and for other environmental and aesthetic reasons. Due to the rapid development of offshore wind farms, submarine cables are also increased and used both for connecting offshore substation to onshore substation, the well-known export cables, or the wind turbine generators between each other, the inter-array cables. In both of them, due to AC current, skin and proximity effects at conductors are developed. The high voltage AC cables are usually in close physical proximity, and this is because many times have space limitations, mostly in underground installations, or because of technical reasons like reduced induced voltages or induced currents. The EMTP software is capable of calculating these induced voltages, induced currents, and other cable characteristics. And a big advantage against other softwares is the inclusion of proximity effect in the latest version 4.2. The goals of the study, as I said before, is the comparison of the measurements that performed from HELLENIC cables for 3 cores 630 square millimeters, consisted of copper conductor insulated with XLPE, lead sheath, and semicon polyethylene jacket. The first sample that we take is an unarmored cable, typical for underground installations, let's say, high voltage underground installations, and it will be examined in trefoil touch information. Then the results will be compared with EMTP. In that case, because of the inclusion of proximity effect in EMTP, we expect to have a good validation between measurement and simulation. In contrary, then we will have a comparison between a submarine cable that is a typical submarine cable, 3 core 630 square millimeters, consisted of copper conductor, XLP insulated lead sheath, semicon jacket, and then polypropylene yarns, mild wire armors with ferromagnetic steel, and again polypropylene yarns. I have to say here that the design is not fixed. For example, the conductor may be with copper or with aluminum, or for instance, for the underground cables, the sheath could be like copper wires with aluminum foil, just a smooth welded aluminum, etc. For the submarine cable, of course, the conductor may be copper or aluminum, and we have the inter-array cables which are screened with copper wires and aluminum foil, and the export cables are sheathed with lead sheath. Of course, the armor material is changed, and it may be with ferromagnetic steel or with stainless steel. In case of submarine cables, the impact of solenoid effects in three-core cable are expected to differ a little bit the measurements to the simulations. As we know, the losses and the losses generated in cables in all metallic parts are very important, and the accurate losses calculation is critical for the right cable dimension. Representative value that reflects all these total losses generated in the cable is the positive sequence impedance. In MOMSO, we can conclude and include in these simulations both skin and now from 4.2 version and afterwards the proximity effects. In general, MOMSO is a two-dimensional approach, but it can be extended to a 2.5D approach, let's say, by eliminating the zero net current in armor wires. And this is very nicely presented in the paper I mentioned below. Then the twisting of power cores and the armor wires consists the problem of submarine cable as a 3D problem in its nature. And thus we have these solenoid effects and a different approximation. Now, regarding the measurements, here we have two pictures of the samples that we checked and measured in our factory from Hellenic cables. The first one is an armored cable, and the second one is the unarmored cable that will be tested. Actually, it is the same cable, but in the second picture, the armor is removed, and it is a typical, let's say, underground cable in Trefoil formation. In the first picture, the sample is placed higher from the ground in order to avoid the interference with the metallic reinforced concrete. And in the second picture, a special corridor is implemented, which is free of any metallic element, and is constructed this way because in the next step, we could measure this as a wet condition cable, and the corridor will be filled with salt water, let's say. In general, in both of these installations, 1 meter free of any metallic element is around the cables to avoid any electromagnetic interference. Here we can see the setup of the cable, a conceptual figure of the measurement setup. The three-core cable, both armored and unarmored cable, is around 36 meters, and the driving end and the earthing end. At the earthing end, all the metallic layers are short-circuited and grounded, and the driving end will have a current injection from a three-phase variac. The voltage and temperature sensors are placed in a position such that that is within the armored section when the sample is the armored one, in order to ensure that negligible end effects from the unarmored part will appear. Then we have another photo of the measurement setup. As we can see, not in the front of the picture, but at the back of the picture, the current is injected via three-phase variac. It is tried to have as much as balanced current injection, but this is not that easy to happen. So some imbalances are inevitable. And on the front side, you can see the brown current transformers, which are calculating and measuring actually the conductor current. And then here, if you see my mouse, there are the blue current transformers where we can measure the sheath currents in case of a solid bonding arrangement, say. The loss estimation is coming through the product of the injected current and the voltage drop along the test sample. Of course, we have used some voltage and temperature sensors. The small wires, the white, black, and brown, are drilled in the conductors and the sheaths in order to have the potential drop between each of them, and the accurate calculation of losses demands accurate temperature of the cable. So RTD platinum type 100 sensor is placed in all metallic layers in order to have accurate temperature measurements. In general, the method that is used in order to calculate the losses is the electric method, where we calculate a positive sequence of current from the current injection at phase A, B, and C. And from these values, we can easily calculate the positive sequence of current. From the voltage sensors, we can have and derive the positive sequence of potential drop. And from these two values, we have, of course, we can derive the positive sequence impedance, which reflects the total losses in the cable and the total complex power in the cable. The real part of this total complex power represents the active power losses, and the imaginary part represents the reactive power losses. Okay. The bonding schemes that are examined and are measured is the solid bonding, where the metallic sheaths are bonded at both ends. This is a representation of an actual bonding scheme, both for typical for underground, let's say, unarmored cables, and for submarine cables, which is the only solution for them. And in that case, we can easily calculate the circulating currents and measure them accordingly. Then we have a single point bonding measurement, where the metallic sheaths are bonded at one end. And this is also a typical bonding scheme for underground cables. And of course, it can be equivalent to the 1/3 of an ideal cross bonding. So we can capture actually all the basic bonding schemes for underground cables. And afterwards, in single point bonding, we can have a good measurement of the induced voltage at the open end. About EMTP simulation now, we have to make a preparation and calculate the inputs that we will insert in our model, the new line cable data model of version 4.2. Firstly, we have to calculate the resistivity at 20 degrees. This is coming from the product of the cross-section and DC resistance at 20 degrees. I have to notice here that this DC resistance is not according to IC standards, but is measured as well in these specific samples from our quality control, let's say. And because strand conductors cannot be represented in EMTP, we have to make an equivalent resistivity at 20 degrees, which is coming from the product of the resistivity at 20 degrees and a filling factor from the geometrical cross-sections to the electrical cross-sections. Afterwards, this is multiplied with an overlay factor because of the twisting of cores. After having this data, we have to make a correction at the measured temperature that we have measured from RTDs, as I showed you before. And this is happened for each metallic layer in order to have an accurate resistivity that we will insert in our model. Of course, all the properties, the equation is the well-known equation from IC standard 6287 part 1, and all the properties like alpha, which is the temperature coefficient per cable at 20 degrees, is coming from the corresponding tables at this standard. As I told you, the length of the samples is short. It's like 36 meters. So the inductive mechanism in our case is dominant. And of course, we have the current injection. So the inductive mechanism is the one that is the most crucial. And we can say that the capacitive mechanism in our case, with a short length, can be neglected. From the following equation, we can derive a relative error between the measurements and the EMTP simulation. And then here you can see the line cable data of version 4.2, a typical, let's say, for underground cable trefoil touch information. The data inputs are as shown in the table behind. And in 4.2 version, the representation of the cables is better shown in the upper left image. Of course, the most important thing is the proximity effect inclusion, as you can see on the right side of the slide. Now, the circuit that is implemented in order to have the measurements and the simulations in EMTP is like this one. Here we have the current sources at phase A, B, and C as measured from the three-phase variac and the CTs. We have the potential difference through these branch voltmeters at each of the phases, phase A, B, and C. A nominal PI device is used to represent the cable, and this is because we have a lumped model because of the short length, and we didn't want to go with wideband, for example, to avoid any fitting errors. So this one, and due to the fact that the inductive mechanism is the dominant one in our case, we can use it with ease at this validation, let's say. Regarding the circuit, the sheaths, as you can see here, are bonded from the right side, and from the left side, and from the right side are bonded together and grounded only from the one side. This is because we want to eliminate the zero sequence part and make not that important the effect of the earth return. So in this way, we avoid to take into account the earth effect. Now, the measurements. Firstly, we show you the voltage drop of the unarmored cable. As you can see here, the voltage drop, we have two diagrams. First, the solid bonding at voltage drop, and then the single point bonding. At the left y-axis, you can see the voltage measured and simulated, and at the right y-axis, the relative error. The three quantities that are examined are the measurement and the EMTP simulation when proximity is on and when proximity is off. In both cases, in solid bonding and single point bonding. The voltage drop with proximity effect gives a much lower relative error, both in solid bonding and single point bonding. And the relative error between measurement and simulation when proximity on is about 6%. Regarding the positive sequence calculation, we have two cases again, the solid bonding at the upper diagrams and the single point bonding at the lower diagrams, where we can have at the upper and left chart the resistive part, the real part of the positive sequence, at the upper right chart, the imaginary part, the reactive power. Here we can notice a very good agreement between measurements and simulation when proximity effect is on. And this is very important because this value here represents the losses in the unarmored sample. Again, for the losses, you can see on the left y-axis the losses in watt per meter, both in solid bonding and single point bonding. A very good agreement between measurements and the EMTP simulation of proximity on is noticed. The relative error is lower than 0.9% in total cable losses. And when proximity is off, the losses are underestimated. And this is something that makes our current rating not conservative. So we can see how crucial is the inclusion of proximity on for unarmored cables. Regarding the solid bonding and single point bonding, we can derive the circulating currents in solid bonding and the induced voltage at the open end at the single point bonding. At the upper diagram, you can see the current in the y-axis that is measured and EMTP with proximity on and off. The circulating currents from EMTP are also in good agreement with the measurement and give a relative error less than 1.6%. In the other case, when we have the single point bonding, the induced voltages have a relative error less than 6.5%, and this makes our measurement and EMTP modeling to be trusted and consider it as a reliable measurement and simulation. Now, regarding the armored cable, we can see here that in EMTP version 4.2, we can have strands in the armored wires. That is very important because this is one step further from the old and the typical pipe type that were used in other software some years ago. This is something very new and important for us, stranding armors. Of course, the inclusion of proximity effect again is very important. And for the armor, which is the latest, the last row in the table of data, you can insert the conductor permeability, which is measured in our case again. We measured it in our laboratory, and we have set it accordingly to the simulation. The circuit of this armored cable is like this. It's pretty much the same with the unarmored cable, that we have the current sources in order to have the current injections as measured from the current transformers in our laboratory. The branch voltages to measure the potential drop at each conductor. The current measures at conductors and sheath currents to have the circulating currents and the conductor currents, of course. And the sheaths are bonded. The sheaths are only bonded. Conductors are grounded only from the one side in order to eliminate again the zero sequence and the effect of the RTL. I have to notice here that in order to ensure that the arm does not include circulating currents, it is open bonded at one end. Again, we have the nominal PI element because of the short length and because the inductive mechanism is dominant. And this is the circuit for the simulation of the armored cable. Regarding the first results now, we have again the voltage drop. The voltage drop for solid bonding and single point bonding. At the solid bonding, we have a very good agreement between simulation and measurements. And the relative error in solid bonding for proximity off is around 2.2%, and when proximity is on, is less than 0.2%. For single point bonding, for proximity off and for proximity off, in both cases, the relative error is less than 6.5%. When proximity is on, we notice that the relative error is lower and than proximity off, and this is indicative of the effect of the proximity effect in armored cable as well. Regarding the positive sequence, we have these measurements. In general, for positive sequence resistive part, we have a 10% relative error and 5% for the reactive part, both in solid bonding and single point bonding. This is because we have the longitudinal component of magnetic field due to the twisting, and this is responsible for this deviation. But for high-grade hours, where the permeability is lower, the deviation is expected to be lower, and it approaches, let's say, the stainless steel armor. Regarding the losses now, the active losses, as you can see in solid bonding and single point bonding, firstly in solid bonding, have a relative error much worse than we have seen before in the unarmored cable. This is because the longitudinal component of magnetic field, which gives a higher relative error than the experimental data. MOMSO is a two-dimensional approach and is not capable of capturing 3D solenoid effects. So maybe this difference is because of these solenoid effects and the armor wires twisting and the coarse twisting. Of course, the relative error is like 10% in total power, in total cable power losses, for solid bond when proximity is on, and around 8.5% when for single point bond when proximity is on. Now, again, for the solid bonding configuration, we have the sheath currents, which give a relative error of 12% when proximity is on and 16% when proximity is off. We notice here that, of course, the proximity effect helps to gather better results, and the higher flux due to the longitudinal field leads to higher induced currents in sheaths than the 2.5D approach of EMTP. So this is the reason why we have a higher relative error than the unarmored cable. For the single point bonding, again, the higher flux of due to the longitudinal field leads to this higher induced voltages than in measurements than the 2.5D approach of EMTP. And this is can briefly describe in the paper that we have, that I noticed here and presented recently in the IPST conference. To conclude this presentation, we can see that MOMSO is in very good agreement with measurements for the unarmored high voltage AC cables. MOMSO, including proximity effect, is a fast and accurate way to calculate losses, induced voltages, and induced currents for unarmored cables with very good accuracy. The accuracy is really very good and high in unarmored cables. When talking about armored cables now, MOMSO with proximity effect is in better agreement, of course, rather than when proximity is off. But in general, 2.5D MOMSO approach with proximity on can capture skin, proximity effect, and acoustic effects, but still cannot account for the longitudinal component of magnetic field driven along the armored wires, and of course ignore the solenoid effects that this occur. So that was my presentation and the validation between simulation and measurement. Thank you very much. If you have any questions,